Howdy. The purpose of this video is to talk about optical properties of materials, and specifically we're going to think about optical emission. We're going to think about LEDs and lasers, and we're also going to talk a little bit about optical absorption, so photovoltaic materials. Now there was a previous video that was talking about absorption of light of different wavelengths and how that relates to the electronic band structure. So if you haven't seen that yet, I recommend checking it out. Okay, as a reminder, we need to think about light as being a bunch of quantized photons. So a packet of light has a specific wavelength, and that wavelength is related to a specific energy. So dependent on what wavelength of light I'm talking about, if I'm talking about something in the visible wavelength, for example, blue and violet has a shorter wavelength but is a higher energy than things in the red, right? Okay, so we talked about absorption before. Now let's think about emission. And in order to get emission, what I tend to need to do is I need to excite an electron from some low level across the band gap to a higher level, and then I need to let that electron fall back down. And when it falls back down, under certain circumstances, I can emit a photon of light. And so in this case, the energy of that photon is going to be dependent on the band gap. So if I look at a bunch of different semiconductors, I could think about potentially tuning what is the wavelength of light that I get out of those semiconductors by mixing different combinations of them. And this is what we call band gap engineering. So essentially, I would take a diode, I would make a diode from this semiconductor, I would excite electrons up to higher energy level, I would let them fall down, and when they fall down, they're emitting a photon of light. That emission is going to be a function of the band gap. So we figured out how to do this a while back, but for a long period of time, we could only do it with things that were in the reds and greens. So we knew there were some materials that would be great emitting in blue and violet range, things like gallium nitride, but we had trouble producing those. And so actually the team that was behind figuring out how to actually grow and make gallium nitride based devices won the Nobel Prize for Physics in 2014. Now, why would that be so exciting? I mean, we already have red and green. Why is blue important? Well, blue is important for two reasons. One is that for any sort of a display, we typically make this by having 3 pixels, red, green, and blue. So without the blue, you can't combine them to get all the colors in the spectrum. But also, remember, blue has the highest energy of all of these wavelengths. So if I want to make a white LED, it's a lot easier to generate high energy photons and to maybe remove some of the energy of those photons, so we're able to emit across a broader spectrum than it is to bump up the energy of photons. So gallium nitride is also behind any sort of white LED. Okay, so that's emission. There's one other thing I wanted to say about absorption, and that's coming back to photovoltaics, right? So the whole point of this is that we would like to put some panel that would absorb photons from the sun and turn those into electricity. And we can do that, and you can tune that panel because you know something about the wavelength of light coming from the sun. So the blue and the green are 2 different measures of actual solar spectra that would be received on the Earth below the atmosphere. But it's a little tricky, right? Because our band gap has a specific finite energy. So we would like to make a material that would absorb as much of this spectrum as possible, but it's tough to do that with a material that just has one band gap. So one approach that some people have taken to doing, and this can give you some of the most efficient solar devices out there, is to make what are called multi-layer junctions. So oftentimes these are 3 or maybe even up to 4 junctions, and each of them is designed to absorb some part of the solar spectrum. Again, because this light is coming in within a fixed range in energy, so we can have the band gap, have it be just small enough to absorb energy within that region of light, of wavelength. So the whole idea behind photovoltaics is that, again, we're tuning this band gap so that we're able to absorb optical light with specific wavelengths. Okay, quickly in summary, photons of light, again, are associated with a specific energy. The wavelength of light that is emitted is going to be dependent on what is that band gap of the material. So we can tune that band gap to some extent, and that's what we call optical band gap engineering. Again, the same thing happens when we're absorbing light. So the wavelength of light that is absorbed is also a function of the band gap of the material. And we use this in a number of different applications, but one great example would be in photovoltaics, where we're tuning that band gap to take as much advantage of the solar spectrum as possible.